Vector databases have become extremely popular in recent years in conjunction with things like large language models. They're perfect for storing unstructured data like text, images, or video or audio files, things which aren't really suitable for a traditional relational database. A common use case for a vector database is giving search or long-term memory support to a language model. So if you've ever wondered how those talk to PDF apps work, it's probably with a vector database. You could use an existing service to host your database like Pinecone or Redis Enterprise, or opt for a free open source solution like pgvector, which adds vector support to a Postgres database. Today I'll go over the high-level concept of how a vector database works, and then the exact flow needed to build a talk to PDF app, which will utilize both a vector database and language model to search through and ask questions on huge documents which would otherwise never fit into a single context window or prompt. So stick around to the end to see that. In a vector database, we don't just store text, we store numbers. These numbers are called embeddings, and they are a numerical representation of the text. I'll explain exactly how these embeddings are produced in a moment, but once we have them, we can store them as points on a graph. So imagine we store the data on a graph with just 2 dimensions, x and y. We produce embeddings for 3 different words: apple, banana, and meteor. Apple and banana would have embeddings which are physically closer on the graph since they have far more in common. So when we search our database with another word like orange, it can return all items in close proximity. So in this case, apple and banana would be a better match than meteor. In reality, vector databases go far beyond 2 dimensions. In computing, there is really no limitation to the number of dimensions we can handle, and most vector databases use thousands of dimensions. So we know how embeddings are stored, but how are they even produced? Well, you've heard of large language models like GPT-4. These models can also produce the embeddings for us, since they're trained on millions of lines of text that can help us capture the true contextual meaning of a piece of text. For example, bank and financial bank would have far more contextual relation than riverbank because of how bank is used in common English, so their embeddings would be closer together on the graph. So we supply a piece of text to the model, and it will return to us an array of numbers. Each number is a coordinate in multi-dimensional space. In our earlier example, we had just 2 dimensions, x and y, so we plot the data with just 2 coordinates. But a model like OpenAI's text embedding ADA002 would return 1,536 coordinates, each representing a single point in 1,536 dimensional space. I know that sounds crazy, but with 2 dimensions, we would only be able to capture very simple relationships. By increasing that number, the model can capture far more complex and deeper context of the data we provide. So now we know how the embeddings are created and how a vector database can store them. Next, let's look at the exact flow needed to use this technology in building a talk to PDF app that you see everywhere online today. So first we have the storage step. The user uploads a document. We then extract the text from that document. The text is split into smaller chunks, which we will store. For each chunk, we request its embedding from a model like text embedding ADA002. We add the embedding along with some metadata, the chunk of text itself, to our vector database. The database will index those embeddings using smart algorithms for efficient storage and later search. So now we have our data stored. How can we search it? So the user sends a prompt. We convert the prompt itself to an embedding using the same model as earlier. We use that embedding to search our vector database. The vector database will return embeddings found in close proximity. Crucially, this also includes the metadata we stored with it. So now we have all the chunks of text which are contextually relevant to our original prompt. We can use those along with our original prompt to send a message to our language model. So I could say, hey, I have this question about a species of penguin found in South America. Here are some documents which may be relevant to the question. And we would provide all the parts of, say, our Nature PDF related to penguins. The AI would then be able to answer my question specifically with data found in the document we originally uploaded. There are many more use cases for a vector database, including search, classification, or anomaly detection. Anything really that can be solved by detecting commonalities in data. I hope this video helped. If you want to see more like this, then please subscribe, and I will see you in the next one.